Hello guys, welcome to my channel. My name is Hitesh Kumar and I'll be taking your Leetcode solutions. So first let me introduce myself. I am in currently BTech third year from CSE. So this is the Leetcode weekly contest 515 and this is the first problem that is nearest available drone. So what does the problem statement says? You are given a 2D integer array drones where drones I indicates x, y and range I, where x, y are the coordinates and range is the travel range where the drone can cover. Like you have seen drones can cover say 1 kilometer, 2 kilometer depending upon their capacity. And you are also given an integer array target which is just 2 points, the target coordinates. Now, what the question says is a drone can reach the target if the Manhattan distance between its coordinates and the target coordinates is less than equal to its range. It's very obvious that if I have a drone which can fly up to some distance, and if the distance that I have to travel is within its range, then it can reach, and if it's out of the range, then it can't reach. So first of what's the Manhattan distance? Manhattan distance is the sum of absolute differences between the x coordinate and the y coordinates. I'll be also showing the formula now later while with the code part. So return the index of the reachable drone with the minimum Manhattan distance to the target. If there is a tie, return the smallest index. Okay, so it's saying that among all the drones that you have in the array, among all of them, return the one with the smallest Manhattan distance. And in case all the Manhattan distance or some of them, the minimum one, there are multiple minimum Manhattan distance, then choose the one with the smallest index. If no drone can reach the target, return -1. Okay, so there can be a scenario where target is pretty far away from the drone and none of the drones in the array can reach there. So in that case, we have to return -1. So here's the first example where you have got drones. These are the coordinates. First one is at 0, 0. The second one is at 2, 2, and the ranges are 8 and 9 respectively. The target is 3, 4. So we have got output 1. Let's see what's happening. So the distance between drone 0 and target is calculated here. So what it's doing is it is calculating the Manhattan distance, that is the absolute of x coordinate difference 0 -3 and absolute of y coordinate distance 0 -4 and adding their sum which is equal to 7, which is in the range of 8. The similar goes to the second drone which gets the Manhattan distance of 3, which is in the range of 9. Now you can clearly see the drone at the first index has the minimum Manhattan distance, so we'll be returning the first index as the answer. Same goes for the second example, where you can find that the first index and the second index both have got the Manhattan distance of 2, but since the first comes earlier, so we'll return 1. In the third example, you can see there is the coordinates and the target. If you do this, you will find that Manhattan distance is 6, but the range of the drone is just 5, so the drone can't reach the target and will return -1. Okay, so let's talk about constraints so we can get the rough idea of what time complexity and other ways we can use. So drone's length can go up to 100. So n square and n cube algorithms can also work here. Drones I will contain XY coordinates and the range. Target will be just 2 points and XY and targets will go from -25 to 25, which is quite low. Since it's an easy problem, the constraints are quite low. We can see the range is from 1 to 100. So let's jump to the code part. Here it is. So we have got 2D array of drones and target array. Now first we'll assign answer as 101. You might be asking why just 101. You can take any value that is some large value incomparable to the distance that might come. Since the constraint were 25 to -25, the max Manhattan distance can be 100. So I have taken 101. Now we have also taken minimum distance, which is equal to int max, or you can take any large value, again the same thing. We have taken n as drone size. Now we'll be iterating the drones array, and first we will calculate the Manhattan distance. That will be absolute of the x coordinate difference and the y coordinate difference over here. Then we'll check if this distance is greater than the range. This is the range of the ith drone. Then we'll continue. We have to skip that part where the target Manhattan distance is greater than the drone's range, and in case it is smaller than the minimum distance, we have to modify minimum distance equal to d and store the index into the answer. At last, we will take care of the edge case where, say, no drone reached the target. So we have taken that if answer remains 101, then we'll simply return -1. In case it changes, we'll return answer. So first, we'll run it for the test cases. You can see it got accepted. Now we'll submit the solution. Yeah, it got accepted with 12.65% beat time. Yeah, that doesn't do anything at all. Okay, so moving on to the second question. This is minimize the maximum waiting time at synchronized traffic light. You are given an integer period and an integer array lights, where lights I is the duration in seconds of the green phase of the ith traffic light. So if you have noticed the traffic light, you will see that there is duration of all these lights. Like the red light will go for 50 seconds, then yellow light for 4 seconds, and the green light for 10 to 15 seconds, depending upon the traffic. So the same goes here. At time zero, every traffic light starts at the beginning of its green phase. So whenever the time starts for the problem, it starts from the green phase of them. Their cycles are synchronized. It means all of them start at once. There is not like that one has a different starting time and the other one has a different starting time. Every traffic light starts a new cycle at the same time, and every cycle lasts exactly period second. So it's like every period second, say the period is of 10 seconds. So after every 10 second, the green phase start for whatever time it is given. Say for the green phase of the first light is for 3 seconds. So it will be green for 3 seconds and then it will go for waiting. Then once the 10-second period ends, it will again be green for the 3 seconds. Now, therefore, the red phase of the ith traffic light will be period minus lights I second. That is pretty obvious that the total duration minus the green phase, this will give you the waiting time or the red light time. You are also given an integer array arrival time, which will indicate the arrival time of the jth car. Say there are 10 cars, so all of them will have different arrival time. Each car must be assigned to exactly one traffic light. That is pretty obvious that you can't assign a car to multiple traffic lights at once. So you have to assign every car and to exactly one traffic light. Multiple cars can be assigned to same traffic light. Okay, so this needs to be taken care that you can assign multiple cars to the same traffic light. As you have also seen that many cars wait at the same traffic signal, waiting for the light to turn green. Any number of cars may cross the same traffic light simultaneously while it's green. So it's not like that why the cars are sequential, that first car will take 2 seconds to go, then the next car might take 3 seconds or 4 seconds. It's not like this. It's like as soon as the signal turns green, all the cars will go. Cars do not block or delay one another. Same thing. For a car J assigned to the ith traffic light, let R is the remaining time, which will be equal to arrival time percent period. Okay, so why we are doing percent period? Because there might be instance when a car comes after the period time. Say the period was of 10 seconds and a car arrives at 12 seconds. So how we can make sure that we find the correct starting point? So that will be equal to arrival time percent period. So say the arrival time was 12 as we discussed and the period was of 10 seconds. So the arrival time for the next cycle, for that cycle where the new car will come for the 12th second, it will be 2. If this remaining distance is less than the light's eye, that is less than the green phase of the light, then the waiting time is 0. That's pretty obvious. If a signal is green and the remaining time is less than that, the car will simply go. On the other hand, if it's not, then the waiting time is period minus R. That is the total time minus the remaining time. The penalty of an assignment is the maximum waiting time among all cars. Okay, so penalty here is defined as the maximum waiting time, and waiting time is where we have discussed is either zero or period minus r. So among all the cards, the maximum one will be the penalty. Okay, so what the question asks is return an integer denoting the minimum possible penalty. So we have to find the answer where we have to find the minimum possible penalty so that all cards can go easily. So this is the first. So one thing that I would like you all to observe is that for let's go with the example so you can understand easily. Here, period is given as 8 seconds. Lights are given as 2 seconds and 3 seconds, while the arrival time is 2, 5, 8, and 11. You can see 11 is greater than 8, so we will obviously use modulo. So one optimal solution is given here, where the arrival time of the first car is 2, and doing that with the modulo will give 2 only, and we'll take the light 3 here. Since 2 is less than 3, the waiting time will be 0. So the penalty is 0. Now for the second light, doing modulo again will give 5. 5 is greater than 2, or if we take the light 3, in this case 5 is still greater than 3. So the waiting time will be the period minus the remaining time, that is 8 minus 5 equivalent to 3. So the penalty now has changed to 3. For the third car, the arrival time, the remaining time is 0. And since 0 is less than 2 and 3, or 2, both of them, the waiting time is 0. The penalty is still 3. And in the last car, the modulo is 3 and 3 is greater than 2. And even if we take the light 3, this one, that will still be equal to 3. So the waiting time will be 8 minus 3 equal to 5. So the penalty becomes 5. And if you try other solution, then still the answer will be 5 to this. So if you notice something that among the lights, if we want to minimize the penalty, then we should take the light that is with the highest green phase. Here it is 3. I hope you are trying to understand that the light with the highest green phase will give the minimum penalty. And the arrival time with modulo period will give a range between 0 to period minus 1, and the 0 to period minus 1 is the constraint for lights also. So choosing the highest light will give the minimum penalty. Let's go with this one. Here the period is 10, the lights are 368. If we take the light 8, now with the arrival time 495, with 4 modulo 10 is 4 less than 8, the waiting time is 0. With 9 modulo 10, 9 is greater than 8, so we will be subtracting it from the period. 10 minus 9, 1, penalty is 1 over here. And for the last light, it is 15, which is equal to 5, and 5 is less than 8, so the waiting time is 0 again. So here you can see the penalty is 1. If you try some other configuration, the penalty will be obviously higher. In the last case, since there is just one light, we have to choose this only. And if you iterate over all of them, you can clearly see the optimal answer will be 3. So here are the constraint where period will be from 2 to 10 to the power 9. The light's length will be 10 to the power 4. So n square might work here. That's not like an obvious case. We will go up to n log n can work, on can work. And the light's I value will be from 1 to period minus 1. Hope you remember that why we took modulo. The modulo will be used here. And the arrival time lengths are 1 to 10 to the power 5, and same for the arrival time value 1 to 10 to the power 9. Okay, so what's the solution? It's an easy one. First, we'll be taking the maximum green time among lights. So here D is the maximum green time, and we have taken the answer as 0. So 0 because the minimum time is 0, and the waiting time was 0 also in case the remaining distance was less than the green time. So iterating towards all the arrival time, we are calculating the R, that is time percent period, for that value. If this R is greater than equal to the maximum element, then answer will be equal to and maximum of answer comma period minus R. This answer is the penalty, and then will simply be returned in. This question is pretty simple than the earlier one. Now we have run the test case, accepted or submitting. Yeah, accepted. So hope you understand.